All right, in this part, I will continue with the kinetic energy. Okay, so I mentioned objects having translational and rotational energy, kinetic energy, uh, while it's rotating. Okay, you should not forget about translational part at all. Okay, so today I will elaborate more about this kinetic energy and then move on to uh, torque. Okay, all right. So let's say we have a wheel, okay, a disc, okay, that is rotating in a counterclockwise direction. Okay, omega is in a counterclockwise direction. Okay, let's say this is the center. Okay, so let's consider a small mass of this disc. Okay, which I'm gonna consider mi. Okay, one particular component. Okay, so this component would be going around in a counterclockwise direction as well. Let's say this is a small part. Okay, velocity is tangential, vi. So ki translational is 1 half mi vi squared. Okay, so vi for that particular object is ri, radius, this is ri, right? Omega squared. Okay, so if we substitute that in here, we get 1 half mi, that should be r times omega, ri squared omega squared. Okay, so now this, I can bring this omega squared outside, so 1 half omega squared. Okay, mi ri squared. So now k disk, okay, let's say for a disk, that is, okay, let me not jump ahead right now. Right now. Okay, let's, so mi squared is your moment of inertia. Okay, so k, kinetic energy rotational, okay, I can write that as 1 half, this is your moment of inertia I, so I omega squared. Okay, similarly for kinetic energy of a disk, okay, that is 1 half omega squared summation of mi ri squared. Okay, this will be the moment of inertia. Okay. So whenever you take the kinetic energy, depending on like you start with k equals to I 1 half I omega squared, and you substitute the value of I in here. If it's a sphere, solid or hollow, depending on that, you put in the values formula for I, which will be given to you. The next one is the torque. Okay, torque is a turning effect of a force. Okay, this is analogous to force in terms of rotation. So if you have a net torque equals to 0, okay, that means the net angular acceleration is 0. In case of force, if the net force was 0, there was no acceleration. Acceleration was 0. That means in that case, object could be moving at a constant velocity or object could be at rest. So in this case, object could be rotating at a constant angular velocity, or could not, like could be completely at rest. Okay, it's a vector quantity. You will have to use a right-hand rule, okay, to find the direction of the torque. Okay, the unit for that is meters times newtons, not nm, because newtons times meter gives you the joules. Meter times newtons. So it's per the cross product rule. So torque here, okay, is r f sine of theta. Theta is an angle between r and f. So in this case, okay, you have, so where is torque applied? In your garage, when you're at your home, like when you're using any tools, you are applying the principle of torque here. So r is your, this is your length of this wrench is your r, wherever you apply the force. Okay, if you extend this, the theta between angle between force and r. So you can increase the rotation, okay, by increasing f or increasing r. Okay, and it depends on the angle. So torque is maximum when theta equals to 90 degrees, because it's perpendicular, right? Sine of 90 is 1. So either you can take the perpendicular component of it, or you can take the tangential component of the force. Okay, it's the same thing. Okay, so in this case you have r f, right? You can write, if you know the angle, or you can take the perpendicular component of the r. Okay, this is the perpendicular, so force is along that. This is the lever arm. R is the lever arm. Okay, so perpendicular component of r, okay, and this is the direction of the force, okay, or force line of action. So line extended through the applied force is called the line of action of the force. Okay, perpendicular distance from the line of action to the axis is called the moment arm. Okay, sorry, this would be the lever moment arm. Okay, the unit is, you can write that as meters times newtons, not. Okay, so door handles. Okay, so for arthritis, like they use doorknob like this because what is this doing is, this is r. Okay, this is your r, moment arm, the force. Okay, sorry, this is not the, I drew my things incorrectly here. Your moment arm would be, okay, this would be r, so you apply the force down. Okay, so if you increase the r, okay, you would have to apply less amount of force. Okay, in those emergency exit doors, okay, you have a handle bar where you push the bar to open the door. So if you try to push towards the where the fulcrum is the pivot point, okay, hinge of the door, okay, you would have to apply more force. However, if you apply the force towards the edge of the door, where usually those door handles are, you would have to apply less amount of force. So we can also write the net torque equals to I times alpha. So F net was mass times acceleration. The net torque is I times alpha. So this is, let's see how we get this. Torque equals to, this is a vector quantity, R cross F. Torque, you can write that as RF sine of theta, which you can write that as R times force tangential. Okay, this is Ft, or torque, you can write that as RF sine of theta. R sine of theta is R perpendicular, so R perpendicular times the force. So let's see how that works here. This is your force, right? So sorry, this is your force here. Okay, so this is your angle phi. So in this case, okay, if this is your angle phi, this would be the perpendicular component, okay, which if we take the parallel to that, that will be force tangent. If parallel to this is this force T, okay, for F tangential, okay, this is along R, okay. This force does not do, this part of the force is not extending because it is parallel to R. Theta is 0, so that means this is not exerting any torque. So this is the part that's exerting torque, okay, that's creating a torque. So Ft is mass times acceleration, so it is in a tangential direction. So torque equals to Ft(r). We can write that as ma, acceleration t, r. Okay, so from the previous part, we know that acceleration tangential is alpha times r, so we can write that torque as ma alpha times r. So alpha, so this is gives you the inertia, so torque equals to I times alpha. Okay, torque net. So in this picture here, okay, so this will be Ft, okay, if I create this component, so this is perpendicular, so Ft, okay, so R phi, R perpendicular is here, so torque is R cross F, okay, torque is RF sine of theta, you can write that as R times Ft, okay, or torque, you can write that as R perpendicular times F, okay, so whichever is convenient for you, okay, acceleration tangential, okay. So as long as you know this is rotating in a counterclockwise direction, so the torque theta is an angle between force and r, so you can either take the perpendicular component of r or you can take the tangential component of force. Ft is m. I'm repeating the same thing I did in the previous slide, so it's a vector, so we cannot forget the vector components. Okay, we'll summation of force, sorry, I said force instead of a torque. Or you can write that as a summation of torque is I times alpha. Okay, so for net torque to be 0, okay, either alpha has to be 0, which implies, right, for that to happen, okay, for that to happen, omega has to be constant, okay, angular velocity has to be constant, so the torque net equals to 0, that means torque clockwise equals to torque counterclockwise. So as per your book, torque clockwise, counterclockwise is given as a positive torque, torque clockwise is given as a negative torque. Okay, so whenever you see the torque in a counterclockwise direction, you consider that as a positive, like you did for forces, clockwise to be negative. Okay, torque measures the effectiveness of the forces at causing an object to rotate about the pivot. So in this case, here is the pivot point. Okay, force is exerted down. Okay, This is your R. Okay. Oh, to be honest, like force is it's in some angle too, not perpendicular. So what we are doing is, so changing gears means like you must have noticed like when you change gears in your bicycle, force you would have to apply increases or decreases depending on how much rotation your bicycle requires. Okay. So here are more pictures of pictorial diagrams for you to understand the torque. So make sure you go over these. Okay. All right, rotational work or kinetic energy theorem states, okay? We'll talk about work energy theorem again. So change in kinetic energy is kinetic final minus kinetic initial. So change in K is K final minus K initial, which is 1/2 mv final squared minus 1/2 mv initial squared, which was work in terms of our linear motion. Work done was in x initial, x final, f dx. So dx. So instantaneous power, okay, P was d omega dt, okay, which was f dx dt, which is fv, okay, constant velocity here, okay. Similarly, in terms of rotation, so x, if you now we are talking in terms of rotation, our x here is, okay, translated in terms of s, arc of a circle. This is your theta, right? D theta is s equals to r times theta. So ds is r times d theta. Okay. So dx in this case replaces dx. Okay. So your work becomes f ds equals to tangential r d theta. So this is your torque. So change in work done is torque times d theta. So P T d theta dt is omega. Okay. So power equals to torque times omega. Angular velocity. So cars are the best examples where this is applied. So in terms of, so engine gives angular acceleration. So engine gives angular acceleration to the flywheel here. Okay, this is the flywheel. So transmission connects flywheel to axles. Okay. So transmission connects flywheels to axles. Okay. So using gears, okay, it provides angular speed to the wheels. Okay. So when we talk about when we brag about our cars, we talk about torque, which determines how much angular acceleration engine can give to the flywheel, whereas power determines the rotational power output of the engine. Okay, that means how fast your engine can rotate. Okay, so torque determines how much angular acceleration engine can give to the flywheel. So whenever you go to a car dealer, they always brag about torque and power, right? So let's see, here's a video like that explains, that shows one of the advertisement where they talk about torque and power. Okay, if you do the comparison, here's a chart here. So this is for 1.8 liter 4-cylinder Toyota Corolla, right? So the maximum power is 132 horsepower at 6,000 RPM, revolutions per minute, right? So if you look at the chart here, okay, uh, torque, right, power is increasing as the revolution goes up, okay. Power is I times omega, so angular, it depends, power is torque times omega, whereas torque stays constant at all angular velocities, okay. So here, okay, we can relate work to power with this equation. So as I have mentioned, like power equals to torque times omega. So if you translate in terms of linear, that'll be FV. So in this chart here, you can see uh, how all our linear and rotational equations are put together. Okay, you can see compare and contrast here. Okay, so please go through this one. So in this case, like this mentions x replaces theta here. Okay, v is dx dt, omega is d theta dt. Okay, pretty much the same concept here. Okay, similar concept. Only thing is objects are rotating now as well, now too. So strings are wrapped around a circumference of two solid disks and pulled with identical forces. The amount of force is the same. Okay, so amount of force is the same. Okay, disk 1 has bigger radius, but both have same moment of inertia. So I is same. I1 equals to I2. Okay, which disk has the biggest angular acceleration? Biggest angular acceleration. Yeah, this is R. Sorry, R1, R2. R1 is greater than R2. So I1 equals to I2. Okay. So same amount of force is applied. So since same amount of force is applied on both of them, so this has greater torque. Torque 1 is greater than torque 2 because this one has a greater radius. Force is the same. So torque 1 is greater than torque 2, right? So I times alpha 1 is greater than I2 alpha 2. Since I1 and I2 are the same, alpha 1 is greater than alpha 2. Okay. So next, we have these problems. I would like you to try both of these problems, okay? Both of these problems, okay, I have put this as a handout, okay? So make sure you go over these problems, and then I will post these slides sometime before this weekend, okay? Before you go on to your Thanksgiving break, okay? More likely, I'll try to put it before your homework is due, okay? Oh no, sorry, this I have not given this homework for chapter 10 yet, okay? Uh, Here's again another slide with some formulas, okay, relating to linear and rotational, and here is an example, okay, another example, okay. So make sure you go over these slides, okay. All right, another question here, conceptual question, okay. Two spheres have same radius and equal masses. One is made of solid aluminum and other one is made from a hollow shell of gold. Okay, which one has a bigger moment of inertia about an axis through its center? Same mass, same radius. One is hollow, one is solid. The answer is B, hollow gold. Okay. Even though they have the same mass, hollow has higher inertia because the mass is distributed far away from the center. Okay. If the masses are close to the center, it will have less inertia. So if you are at the gym, okay, if you take a dumbbell and you try to rotate it, okay, rotate it, okay, you grab it at the center and then you put it in front of you and try to rotate it vertically, okay, you will have if the same mass, let's say same mass dumbbells and same mass barbell, you'll have a hard time rotating a barbell because masses are is those masses are far away from the center, so a moment of inertia is high for that barbell compared to the dumbbell. Okay. All right, that's all. If you have any questions, please let me know, and then I'll be posting solutions to those handout as soon as possible. Okay.